is what it means. You need to keep this interpretation of the p-value with you. This needs to be ingrained in you. In the future, you're going to be reading some kind of paper, and it's going to have like, oh, you know, this medication is effective, and here's the p-value. And if you default immediately to this interpretation of the p-value, then you'll know exactly what they're talking about, right? Because you know, their initial hypothesis would be something like the medication, you know, is effective, the treatment is effective, and then the treatment is effective, and the p-value for our study was 0.003. That's a really low chance of if we reject that hypothesis that the medication is effective and their p-value is that low, then we're pretty confident that we're right, that it is not effective. So of course, you would have to know what their initial hypothesis is. It could be that on the other hand, it could be that the treatment is not effective and they have that low p-value. Then rejecting it would mean that the medication is working. So we always would need to know naturally what their initial hypothesis is, and that'll always be stated very plainly at the beginning of the paper. And what we're doing today is another hypothesis test. I promised to you that we would be doing hypothesis testing for the rest of the term once we started it. And so let's recap. First, we did hypothesis test about a mean. We did hypothesis testing about a proportion, P. We had a hypothesis test about a population correlation coefficient, rho. And finally, today we will do a hypothesis test that concerns a difference of two means. This test is extremely useful because let's say you had, well, the medication one's a good one to stick with. So maybe it's blood pressure medication. And before treatment, we had an assumption about what blood pressure in our population of patients would be, and then after treatment, there's a different. We would believe it should be lower because it's blood pressure medication. It shouldn't be raising it; it should be lowering it, and then we can test a claim about what the difference in these two numbers should be. So maybe the drug manufacturer says, on the average, you could expect, 10-point reduction. And then so, then that's what they would claim this to be. Just like up here, they would have claimed some mean. The average average blood pressure is or average blood pressure is 120, and then you can take a sample and check to see if that number 120 is correct. So down here, maybe we have a drug that treats blood pressure, and so the change should be 10 points, let's say. Then I can have a sample. I can take everyone's blood pressure before treatment and after treatment, and then get a difference in two sample means, and have this number that's a difference in two sample means. Compare it to, and I'll just create a test statistic that's just like a test statistic for here or for here. This one is special. We never saw the test statistic for this, but the test statistics for each of these, even this one that you didn't see, has the form of a z-score. The test statistics every time had the form of a z-score. And what was that form? What was a z-score? What was our first definition of the z-score?
Mean minus mu over x
Sigma.
sigma, that's right.
And what are these symbols? X.
Bar, sorry.
Well, that was when we were doing a. So when we originally said, here's what a z-score is. This first number was an observation. This is what we saw happen in our sample. We saw some particular, remember the problem we did was with the heights. It was with the tallest guy and the shortest guy. And we observed that the tallest guy was this tall, but the average height of men at that time was mu. And the standard deviation of height of men was sigma. So this first number is an observation, and then we subtract away a mean. And we have a name for this, the observed minus the mean. What is that? We talked about it last week. And
Sample?
the week before? No? We've been discussing this numerator since week 3. It's the deviation. It's the deviation. And the thing in the denominator is the standard deviation. So the z-score is just a ratio of two deviations. It's this particular deviation that's associated with this observation compared to the standard deviation. So in essence, the z-score is a ratio of two deviations. That means that a test statistic in its most fundamental, or not fundamental, but generalized form is just a z-score. It's just a ratio of two deviations. When we elevated this idea to our first test statistic, it really was a z-score because we looked it up on the normal curve, and that was when we observed x bar, right? We saw in our sample that it had an average, and we took that away from the population mean, and used this thing as our standard deviation, which sort of came from the stuff we did in week 5 having to do with the central limit theorem. But there it was sigma over root n because we knew sigma. But by the time you're doing a hypothesis test, you don't actually know mu or sigma. So you make an assumption about what mu is. We assume it to be true, and we have to use the sample standard deviation as our estimate for what the population standard deviation would be. And that turned out to be a z-score. If it was, and that was if we were doing hypothesis testing about a proportion. Sorry, I messed up here. This is a mu, and so this wasn't a z-score, it was a t-score, and that was about a mean. If it was about a proportion, then it's a z-score. And it had the same format. We observe some p hat. That was the proportion that we saw happen in our sample, minus what was the claim of the average proportion. And then it was divided by this standard deviation of the proportion. So I'm driving home this idea that our test statistic is nothing more than something that has this general form. The deviation over the standard deviation. And when we did this hypothesis testing about a mu, we also had this special degrees of freedom idea. And back then it was easy, it was just n minus 1. All right, now it's going to change. Because it's going to be, there's more than one category now, right? You're going to have 2 different means, and so the degrees of freedom is a much different number. Here we're talking about the difference of 2 means. So our test statistic still needs to have the form of observed minus the mean. And let me exchange this word mean for something else, because what we say when we mean mean is it's like the expected. This is where we expect to see it. You would expect to see something near its mean. So the observed minus the expected over standard deviation. It's going to have this form. Now, if I'm looking at two samples, over here I have a sample of students from last year, and then over here I have a sample of students from this year. And I look at like their average grades, right? So I have, on the one hand, I have the average grades from last year, and here I have the average of the grades from this year, and I want to look at the difference of those 2 things. So I might say, or I will say, that the thing I observe is this. That's my observed value. That's the difference between the average grades in each of those 2 years. And then mu1 minus mu2, well, that's the difference that we expect to see between those 2 years. Mu1 minus mu2. Now, if my expectation is that there shouldn't be any difference at all, then this quantity here would be 0, because they're the same number. If I didn't change anything and the students aren't different, right, then mu1 minus mu2 would be 0, because there would be no change. It would be like the climb. So I might say the initial hypothesis is that mu1 minus mu2 equals 0. In fact, all of the problems you do today will have mu1 minus mu2 equal to 0, but it does not have to be. It could be like what we were talking about with the change in blood pressure medication. mu1 minus mu2 is 10 points on your blood pressure or something like that. So here I have this numerator, and it's got the same feeling as a regular old deviation. The thing I observed minus the average I expect. And then, so down here we should have a standard deviation that feels pretty normal, even if it looks weird. And if you think, I'm going to have 2 standard deviations, one of them for each of these samples. So I'm going to have, like an S1 over square root of N1. I'm going to have an S2, don't write this yet, over square root of N2. Right? It would have looked just like that. That's what we had right down here, S over root N. But I've got 2 of them now, so I got to do something that is like an average. And if you think back to the way we did our average when it came to variance, we said let's square everything, then add it up, and then take a square root. When we add it up, divide by everything, and take a square root when we're done. Now, you wouldn't be dividing by, so you might say, okay, well, S1 plus S2 over N1 plus N2. Maybe this should be the average of those 2 numbers, but it's unfortunately not that simple. N1 plus N2 would definitely be how many people you had altogether from both samples, but you don't. The size of sample 2 doesn't have anything to do with the standard deviation of sample 1, so you can't take the average in this way. But what you can do is, like I was saying, if we square both of these, if I square this one and square this one, then the radical in the denominator won't be there, right? Because the square root of something and then you square it is just that something. So if I square both of those, then I won't have a radical in the denominator. So it'll be S1 squared over however many people are in the first group. And then I can just add that to S2 squared over however many people were in the second group. Now, standard deviation squared is what? Like I have this written, the standard deviation of the first group squared, but that has another name. What was the definition of standard deviation? How did we derive that standard deviation? First, we had to build this difficult thing. And then we said, oh, the standard deviation is just variance. And we said that the standard deviation, what did we say? We said the standard deviation is the square root of the variance. So if I square both sides of this, then the standard deviation squared is just the variance. So this object right here is the variance of the first sample, and this number here is the variance of the second sample. So now that I'm back to dealing with variances, then this quantity here is very much similar to well, it's just the variance, and then so remember the variance was the sum of all the squared deviations, and then you divide it by n minus 1. So then this thing is like, the numerator has the sum of the squared variances, or sum of the squared deviations, and then it's divided by n1 minus 1, and then it's divided by n1 again. So you have this number, you add it to this other number, you take the square root, that is the standard deviation of this joint. It's this joint deviation of these two means. Now, if this looks complicated, you ain't seen nothing yet. Because we would have to have a degrees of freedom associated with this. And the degrees of freedom was just n minus 1. And there are two, so if you're ever using an online calculator in the future, they might say to you that the degrees of freedom is just n1 plus n2 minus 2. Because you would have the first one minus 1 and then the second one minus 1. But this is only for if the two groups have equal variance. That would require you to have S1 and S2 be pretty close to the same number, or at least knowledge that they're reasonably close to each other. Then you could use this. But in most cases, this degrees of freedom is inadequate. It is not, you would say it's not robust. Because the likelihood that these two numbers, sorry, I misspoke. This should be for equal population variance. I might have these two numbers, S1 and S2. S1 squared, S2 squared, these are the sample variance of my samples, N1 and N2. But this doesn't tell me anything about the population variance, which is something I don't know. I don't know what the population variance is, unless I've gone out and checked every single member of that population. And you could only use this degrees of freedom if you knew that each of those populations had equal variance. And if you don't know that, then you have to use this other degrees of freedom. using this, correctly using this is rare. It hardly ever happens. For your entertainment, I will show you what the degrees of freedom is for unequal variance, which is the one that we have to use in every problem for today. So the degrees of freedom for unequal variance and I'm sure there's a way to argue that this is somehow reasonable, but I don't think I've ever figured it out. S1 squared over N1 plus S2 squared over N2. You take this whole thing and you square it, and then it's divided by S to the fourth, S1 to the fourth over N1 squared times N1 minus 1 plus S2 to the fourth over N2 squared N2 minus 1. Now this is an unpleasant computation. Much, much more sophisticated. Fortunately for us, StatCrunch is going to compute all of this like that. I don't care if you write it or not. This number, though, is if let's say you go to graduate school, you're going to become a nurse practitioner or whatever. You'll need this, right? I was tutoring someone getting their DNP, and the statistics class that they were taking was very involved. I mean, I had to like do a bunch of research on stuff just to be able to tutor them. So, you know, if you ever do find yourself needing to use this formula, it would be several years down the road, and you can easily get it from the internet. I don't have it memorized. I had to look it up, but you have to know what you're looking up. You have to know that you're needing the degrees of freedom computation for when I do not believe or have no reason to believe that the variance of each sample should be the same. When they're unequal, it's this complicated formula. If they have the same variance, then it's just the sum of the two numbers minus 2. Here's our login code. So all of this test statistic gets computed by StatCrunch. Many times this quantity is just 0, especially if the question is just, did these two samples come from the same population? If I have this sample and then this sample, and they have some, you know, surely their averages are different by just a little bit. My question might be, did they come from the same population? If they came from the same population, then N1 and N2 are the same number. So this quantity would be 0. So oftentimes this thing simplifies, and you can only use this degrees of freedom if you know the population variance for each is the same. Other than that, everything else is the same. You would use this test statistic. You'll get a degrees of freedom. This would be the degrees of freedom. You would type that into your T calculator. You would type your test statistic into your T calculator. You're going to get some kind of area in the tail. That area is a that area is a p-value. modulo if it's a two-tailed test or a one-tailed test, maybe you have to double it. Then immediately after conducting the hypothesis test on today's questions, you would build a confidence interval. And then they're going to ask you, does it agree with the hypothesis test? Now, I want you to suppose that we had conducted our hypothesis test and we had done everything correctly. All the computations are correct, we got all the correct numbers. And then suppose that we did our confidence interval, did everything correct, got all the correct numbers, no errors anywhere in our computations. Could we then answer this question? If I didn't make any mistakes in my confidence interval or in my hypothesis test, I want to be able to answer this question and give a reason why. So if you think back to how did we, in week 6, how did we get the test statistic to begin with? Because the confidence interval, that's what we did in week 5. It gives us a range where we think that the parameter should live, like the mean, or maybe it's the difference of these means, or maybe it's the population proportion. We get an interval where we believe the parameter lives. That was a confidence interval. The hypothesis test needed a test statistic. Where did that test statistic come from? So here is a confidence interval. This is a confidence interval for mu. This bunch of writing says that mu lives between these two numbers to what degree of confidence? That degree of confidence comes from, it is associated with this. However confident we want to be, this number depends on that confidence. Such that if this number gets bigger, then it's going to multiply by this and make the quantity that we're adding and subtracting get bigger. That makes the interval get wider. That way we can be more sure that mu will live in here. If I have a very wide interval, then naturally I should be pretty confident that mu is in there. So if our confidence level is increasing, if I wanted to be 99.9999% confident, really, really confident, then that would give me an area in between two numbers that's 99.99999%. Well, that means those two numbers are going to be pushed way out away from 0. Those two numbers are this. It's just the positive one. So that means that this number is far from 0. The more confident I need to be, the further this number gets from 0. That makes the interval stretch wider and wider. But all of the symbols that we need for the hypothesis test are right here. Because remember, we did some algebra. What did we do? We just solved this so that the only thing on each side was the t sub alpha over 2 and the minus t sub alpha over 2. We just did algebra, 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 and then the thing in the middle became x bar minus mu divided by s over root n. And on either side was plus or minus t sub alpha over 2. This is the connection between the confidence interval and the hypothesis test. In the event that, so we would be some degree of confidence that this statement would be true, that mu really would live in between here. And if nothing changed between here and here, it'd be the same level of confidence. And then all that changed is now somebody has said, suppose that such and such is what mu is. Is it pretend it's this number? Then, if this statement holds and our test statistic is between these two numbers, then we could be confident that the assumption that this was correct really was correct. Because the assumption that this is correct is what H0 is. H0 is mu equals whatever. And this test statistic would be in between t sub alpha over 2 and minus t sub alpha over 2. That would not result in a p-value that's really small. This would give you a p-value that's really big. You would have let's say that t sub alpha over 2 is right there. You would have minus t sub alpha over 2 over here. This area that's in these tails would be alpha. Well, if my test statistic is coming out in the middle, let's say it comes out right here, at this blue dot, then my p-value would have been an area that's a lot bigger than alpha. So I would have this picture shows you that you would have a if this really happened, if this down here really happened, then you would have a violation on the restriction of the amount of risk that you could take. The blue area is bigger than the yellow shaded area. The yellow shaded area is the maximum amount of risk that you can take if you want to reject. Well, this picture shows you that the blue area is our p-value, and so it would be very risky for you to reject the initial hypothesis here, so you would fail to reject. This is a picture of fail to reject. That's what happens when you have this statement be true. And it comes from this true statement. So, does the hypothesis test agree with the confidence interval? Why would you think it would be in a particular case?
Based on the example you showed, you said it's outside of the restriction.
So, excuse me. So let's assume that that we did this confidence interval and that it was right. That somehow later on we checked and found out, oh, mu really is in between these two limits. Okay? So we know that this is true. If all I did was algebra to get to here, shouldn't this also be true? Yeah. If I didn't make any algebraic mistakes, then this would also be a true statement. If this is a true statement, then you have this scenario where the test statistic is in between the 2 t sub alpha over 2's. Right? Here's my test statistic, and here it is in between plus or minus t sub alpha over 2. So it's like, that's my test statistic right there. And this is the positive t sub alpha over 2, and this yellow line is the negative t sub alpha over 2. And so the blue shaded area is my p-value, which is too big. It's bigger than the yellow shaded area. So I would fail to reject. That means I'm going to keep the initial hypothesis. And what was the initial hypothesis? It's that mu equals such and such, whatever number. So if this is true, and this was true, and we found that, and this meant that we would fail to reject because mu really was equal to whatever number they said, and we really had trapped mu in between these two things here, then in every case, no matter what has happened, they must agree. They came from each other. They agree for no reason more than, if you assume this is true, then this must also be true. And if you assume that this is false, then this must also be false. So no matter what happens, every time, the confidence interval and the hypothesis test agree with one another. And they must agree with one another because the test statistic came from the hypothesis test. I had an idea the other day about how I could finally remedy my problem of never having enough room on the screen. So I want to try something. numbers or? I thought it would be easier than this. Lost this window. Oh well. I'm wanting to regain all of this real estate up here. It's just drives me crazy. Does giving candy to dining parties result in greater tips? I guess if you're a server. Then if you have 40 tables, gave 40 tables no candy. This is the average tips, standard deviation of the tips. In the second group of 40 tables, you gave them 2 candies. Average tip, I think it's kind of big. Average tip, I don't know what they ordered, but average tip and standard deviation. All of this other words about assume that it's independent, random sample from normally distributed populations. That's stuff that you have to have be true before you can do this test. It will be true in all of our problems. And then look at this here. Do not assume that the population standard deviations are equal. That would mean that the variances are not equal for the population, so you would have to use that complicated degrees of freedom. If you went to the view an example, what would they tell you in here? They'll be showing you the wrong stuff. Why is it wrong? There's our test statistic. That's at least right. So they would say to you, here's the formula for the test statistic. There it is. That you can use either technology or the formula. Here we're going to use the formula, and they get this number for their test statistic. And then they're saying they have this for their degrees of freedom. That's not right. because they were supposed to not assume that the variances were equal. So it would be challenging to try to do this with their help. It's not, the people who wrote the Help Me Solve This and the View an Example are not the author of the book. One more thing before we get started. In our test statistic, we had this term, mu1 minus mu2. Right? That was the difference of the two population means. And what are they having us check here? Test the claim that giving candy does result in greater tips. So if it's going to result in greater tips, then you would have, for your initial hypothesis, that there would be no change, that it would be the same. If giving candy resulted in a greater tip, then you would have mu2 be bigger than mu1. Mu1 minus mu2 would be less than 0. You understand? Yeah.
So it's opposite for the last one.
Careful now. It's not opposite. Mu2 is the average tip when you give candy. If I'm going to take away from mu1 a number that's bigger than mu1, shouldn't it be negative? Yeah. So it's not opposite. It's exactly what we expect. If the average tip for no candy was $20, but this was $22, then that's a negative 2. So it'd be less than 0. Now, this writing, this is how StatCrunch looks at it. Okay? This is how StatCrunch looks at it. But in the homework, what they have done is an equivalent statement. Just add mu2 to both sides. And then you get mu1 equal to mu2, mu1 less than mu2. Where the second one says the people who got candy tipped more than the people who didn't get candy. It all means that both these mean the same thing. So, for our initial and alternative hypotheses, well, it can't be A, because A does not have an initial hypothesis that's got an equal sign. In fact, I can see it already that it's B, right? Because B is exactly what we wrote right here. B has the alternate hypothesis that the second group, which is the group that got candy, has a bigger tip average than the people who didn't get candy. Now they want the test statistic. I'm going to go to Get More Help and open StatCrunch. Stat, T-stats, 2 sample, with summary. That's stat, t-stats, 2 sample with summary. They want to know all about your summary table. All right, sample 1 is going to correspond to the one that has the subscript of 1 here. So the sample mean for the group that got no candy was 19.26. with a sample standard deviation of 1.39, and it had a sample size of 40. For group 2 that did get candy, the sample mean was 21.89 with a standard deviation of 2.34. The sample size was also 40. When I scroll down, it should be pre-selected for a hypothesis test. The difference in the 2 means is 0, just like we said in our original setup. The difference of the 2 means is 0, but mu1 should be less than mu2. So mu1 minus mu2 should be less than 0. And when I click compute, it's going to give me everything I need to finish the problem. Well, everything I need to finish part A. Look at that wild looking degrees of freedom. It's not an integer anymore. It calculated my degrees of freedom automatically. It calculated my test statistic automatically. It went and looked on the T chart, on the T calculator with this degrees of freedom, and it put in this test statistic and told me what the area was in the table past that test statistic. So all of it's done. I've got my test statistic, I've got my p-value. To 2 decimal places, my test statistic is minus 6.11. That p-value to 3 decimal places was just 0 because it was so small. That means there's an extremely low probability, a near 0 probability, that I would be wrong if I reject H0. So I'm going to reject. I have sufficient evidence that shows that giving him candy results in bigger toes. Now that's part A. How are we doing on part A? Don't close StatCrunch if you finish part A. Don't close it, leave it open. Did you finish part A? Okay.
It said fail to reject.
No, not me, because my p-value was 0. P-value is the probability of being wrong if you reject. If the probability of being wrong is 0, then it would not be smart to do the opposite of reject. Right, so extremely low probability of being wrong if I reject, I'm going to go ahead and reject. What's your p-value?
0.
0. So you also reject. Now, when you finish part A and you've still got StatCrunch open, click Options, Edit. If you click Options, Edit, it opens the window back up with all your numbers still typed in. That's going to be handy. You scroll down to confidence interval. What we need to know is what the confidence level is. Okay, well, the confidence level was dependent on the significance level. There's two cases. And here, in these two cases, there is the opportunity to use that word opposite that you were wanting to use. When I have my if I'm doing a one-tailed test, if I'm doing a one-tailed test, then the significance level is that. It's alpha. That's the significance level. If I'm doing a two-tailed test, then you have split your alpha into two pieces, and you have over here you have alpha over 2, and then over here you have alpha over 2. And it was this region in the middle which was the confidence level. This region in the middle was our confidence level. So if I have a two-tailed test, then my confidence level is 1 minus alpha. That's what this picture says. But if I have a one-tailed test, I still need the confidence level to be a region in the middle. So you have to put another alpha over here on this side. So that way it forms a symmetric region about the middle. Then the confidence level, the part here in the middle on a one-tailed test, would have to be 1 minus 2 alphas. And then there's this sensation that there's an opposite, because this is 1 minus 1 alpha, and that's a two-tailed test. But for a one-tailed test, it was 1 minus 2 alpha. You see what I'm saying? Now, we are doing a one-tailed test. So for us to find the confidence level, we need to find whatever our significance level alpha was, and then the confidence level will be 1 minus twice that significance level. Our significance level, we are told, is 0.01. It's a penny. $1 minus 2 pennies is our confidence level. It's 1 minus 2 of these. So it's 0.98. My confidence level is 0.98. It's 1 minus 2 times 0.01. $1 minus 2 pennies. .98 for my confidence level. And compute. It gives me a lower limit and an upper limit.
Did you say 0.98, or what did you say again?
0.98 was my confidence level. Because it was 1 minus twice the significance level. Significance level is 0.01. Well, here is my confidence interval. The bottom number is minus 3.657. The upper number is minus 1.60. It does not contain 0. It does not contain 0. So that means that we're 98% confident that whatever the difference in these two means is, it's going to be negative because it's in between this negative number and this negative number. And what did having this difference be negative mean? It meant that the people who got candy tipped more because they were group 2. And that matches what we did in our hypothesis test. Because the outcome of the hypothesis test was that we rejected H0. We rejected the idea that they were the same tip amount. Instead, we had reason to believe that the tip amounts were different and that mu2 tipped bigger. And that agrees with the findings of our confidence interval. Yeah.
What was your question for A? I thought it said that greater than minus equals.
Yours says test the claim that giving candy results in equal tips.
The samples are from the same population.
Right here in this, it says same population.
Yes.
Then you would have a not equal symbol, right?
Yeah, no, that's, yes, I have that.
So they want my confidence interval to 2 places. So it's minus 3.66 and minus 1.60. That is telling me, so the hypothesis test told me that yes, the people who got candy tipped more. The confidence interval is telling me that how much more they tip. It's somewhere between $1.60 more and $3.66 more. How sure am I that it's between these two numbers? I'm 98% sure. Finally is the last question. The question that if they dropped us off from outer space and said and didn't let us look at any of the rest of the question, we could answer this one every time. Yes, they agree. Does the confidence interval support the conclusion of the hypothesis test? Yes, it will always support the conclusion. And in this case, it would support that conclusion because the confidence interval contains only negative numbers. That confidence interval containing only negative numbers means that mu1 minus mu2 is negative. And mu1 minus mu2 means mu1 is less than mu2. And that's what our alternate hypothesis was. That's the end of this question. All right. Did we all get it?
Yeah.
More or less. Really, that's it? You got it?
Oh, yeah.
So what's up?
Is the next question just like this one?
Yeah, they all.
I'll just-
You
Sure, I'm standing right here.
I lost track of what you did, because I had to go back and put my numbers in the correct way. I had them backwards, so I got behind. So once I have a two-tail, so it's 1 minus my alpha, which is 0.10, which ends up being 90. I didn't know what you did after that. Because you must have come in here and changed the
Scroll up and
confidence level.
scroll up.
This one?
Yeah, I want to see the instructions in part A. All right, scroll down. And so this being a two-tailed test, you already have the two tails. So your confidence level is just 1 minus alpha. It's that.
Yeah, I put this in there.
Yeah. And they want to 3 decimals, so minus 0.656 and minus.
Oh, I did not see
You don't have a minus. They both need to be negative because if it contains 0,
that. Yeah, I didn't see it.
if the confidence interval is containing 0, then that would necessitate the hypothesis test being mu1 equals mu2, which would be a fail to reject. Let's take a break. We'll take 10 and then come back, and these next 4 will be like nothing. You can try them if you want to. 2 is the placebo group. Can you tell that from the table? Column treatment is associated with mu1. See it from the table? Okay. And they've asked us to check to see if the 2 samples come from the population of the same. So the initial hypothesis is that they have the same. mu1 is equal to mu2. And then the alternate is they're different. What are those symbols in mu, x bar, s? What are their names? N is the sample size. N is the sample size. X bar is the sample mean. And S is the sample standard deviation. Treatment group, placebo group, a common type of test for a difference of 2 means test. We don't even know what they're treating, doesn't matter. However they measured their outcomes, the treatment group had a lower number than the placebo group. So maybe they're trying to, this could be a medication that I don't know. Can't think of anything that would have that if it was effective, it would have a lower number than placebo. Maybe it's an antibiotic. And somehow this is like a measure of bacteria colonies in some wound or something. And if you got treatment, then you had less bacteria than if you had the placebo. But there's this standard deviation involved, and naturally this one has a bigger standard deviation, so we wonder if they'll actually overlap with one another such that the difference between the 2 of them is really not statistically significant. So we're checking to see if they come from the population, if they come from populations with the same mean. So the alternate hypothesis is just not equal to. T-stats 2 sample with summary. Then for the first group, my sample mean was 2.37, standard deviation 0.65, and the sample size was 25.
notice here that the sample sizes are different. You actually do not need the sample sizes to be the same in order to do this test. Sample mean 2.67 with the standard deviation 0.92. We're doing a hypothesis test. It's that they come from the same population or they come from different populations. I've got my test statistic, I've got my p-value. To 2 decimal places, my test statistic is minus 1.52. To 3 decimal places, my p-value is 0.135. That's a big p-value. It's a 13.5% chance I'd be wrong if I reject. I don't like to be wrong, so I will fail to reject. Every time I fail to reject, it's because I do not have sufficient evidence. Look at what this says. It says, fail to reject. I don't have sufficient evidence to reject. It's a very obvious thing to say. The evidence to do so. Then they want the confidence interval. So you go back to StatCrunch, and you click Options, Edit. It opens back up your window with all your same numbers typed in, and you can just scroll down, switch it to confidence interval, and all you need to do is figure out what that confidence level should be. Well, here they're telling me to use a significance level of 0.10. And it's a two-tailed test, so our confidence level is 1 minus alpha. That's 1 minus 0.10, that's 0.9. Confidence level,
Will you explain why it's a two-tailed?
Yes. It's a two-tailed test because it's not equal. Because when it was two-tailed, like we still have alpha, whatever alpha is. In this case, it's 0.1. But because it's two-tailed, we're checking both of these. We have to take alpha and split it into 2 pieces. So we already have that symmetric interval. All right, then I'm ready to do my confidence interval at this confidence level. And I get my lower limit and my upper limit. Now, what did I do on my hypothesis test? On my hypothesis tests, I failed to reject. So failing to reject was to say that mu1 and mu2 were the same. If mu1 and mu2 are the same, then that means they could be equal. And then now look, here's my confidence interval. So mu1 and mu2 are between this negative number and this positive number. And what's in between this negative number and this positive number? 0. So we're saying totally plausible that their difference could be 0. In fact, we're 90% confident that their difference is 0. Or any of those numbers between minus 0.6 and 0.03. To 3 decimal places, I would put minus 0.631. And positive 0.031. How are we doing?
Good.
Well, it depends. What was your significance level?
It was
Okay. Use a two-tailed test. So your confidence level would be 1 minus the significance level.
so
It would not be times 2. It would not be times 2 because it's a two-tailed test. If it's a two-tailed test, it's 1 minus 1 alpha.
oh sure.
If it's a one-tailed test, then it's 1 minus 2 alpha. Okay. Number 3. Magnets to treat back pain. So somehow they have to quantify pain level, and I'm sure you've seen the chart in the hospital where it's like got the smiley face, and then the face keeps getting worse and worse, and the color keeps getting red, more and more red, until finally it's pain level 6, and smiley face is a frowny face, and it's all red. So something along those lines is what they've done here. And we have our results from these 19 patients in each group. In the first group, they treated them with magnets, and in the second group, they just had like a hunk of metal, I guess, a placebo. Here I have a 0.05 significance level. And they want me to see if the treatment group has a greater reduction in pain than the placebo group. Now the treatment group is mu1, and the placebo group is mu2, so my alternate hypothesis will be mu1 greater than mu2. Right? Because the X bar is a reduction. X bar is the average reduction in pain level. right, so the average reduction in pain level for the treatment group was 0.46 with a standard deviation of 0.87 with 19 people. And the placebo group was 0.36 reduction with a 1.5 standard deviation. It's big standard deviation with a sample size of 19. This is my hypothesis test, equals 0, greater than 0. And so I get my test statistic and my p-value. Now that's an enormous p-value, 40% chance I'd be wrong if I reject. So I would fail to reject. And what am I failing to reject? I'm failing to reject the notion that mu1 and mu2 are the same. I'm not going to throw that away. I'm going to keep that idea that mu1 and mu2 are the same. So if I'm keeping this, then I'm saying there's no difference between the treatment group and the placebo group. Then when I go to conduct my confidence interval, I need my confidence interval to align with this. For my confidence interval to align with this, the difference between mu1 and mu2 should be plausibly 0. That would necessitate the lower limit being negative and the upper limit being positive. So that way 0 is in the interval. So when I go to do my confidence interval, I'm going to have a negative number and a positive number. Test statistic is 0.25. P-value to 3 decimal places, 0.402. Fail to reject. There is not sufficient evidence to warrant or to support the claim of the alternate hypothesis. Construct the confidence interval. What? Construct the confidence interval. I'll go back to my StatCrunch. I'll say options, edit. All my numbers are still there. I can switch it to confidence interval. And I need to know what my confidence level was. So my confidence level, or excuse me, my significance level is 0.05. This is a one-tailed test, right? A one-tailed test means my confidence level is 1 minus 2 alpha. And since alpha is 0.05, it'll be $1 minus 2 nickels. So my confidence level is 90 cents. Notice that my confidence interval contains 0 because the lower limit is negative and the upper limit is positive. To 2 decimal places, be minus 0.58. And positive 0.78. Does it appear that magnets are effective in treating back pain? No, it does not. Is it valid to argue that they might appear to be effective if the sample sizes are larger? That's kind of a not the greatest question. Because common sense tells you, no, you could have a sample size of all the people on the planet, and you're not going to ever be able to show that magnets are more effective or effective at all. It's pseudoscience. However, so this is a two-part question. So the first part is going to answer the first question. It can't be D, because if the p-value is less than the significance level, you would have rejected. And then now they ask you the second question. Is it valid to argue that you could possibly show effectiveness if you had a larger sample size? Well, think about that for a minute. Appropriate sample size. Appropriate sample size will come from the computation of the confidence interval. So if I were to study my original formula for confidence interval, x bar plus or minus t sub alpha over 2 times s over root n. If I'm looking at this thing, and I think I can say, let me say if I want this to be less than so the thing is that our sample size is right down here. So it's like you can solve this thing for the sample size, but it's gotta be in relation to something over here. And I'm thinking, we'll do it like this. So this is our margin of error, right? We're taking X bar plus or minus that. That's my margin of error. Was there a question on the midterm that talked about appropriate sample size? They finally take it off? I mean, you would have missed it because and complained, I would expect, because we never talked about it. What am I forgetting here? Let me see. Can't do it in my head. Don't write this. So, yeah. Got it. Got it. The confidence interval is X bar plus or minus the margin of error. I can decide up front how wide I want my confidence interval to be. So I might say, well, let's have this confidence interval have a margin of error of just like 0.1 or something. So I might come here from the outset and I say I want that interval to be no wider than 0.1. I declare, I set this. And I decide that I want my confidence level to be, 90% or whatever. And I would compute my sample standard deviation. This writing right here is the margin of error from the confidence interval. And if you just solved it for n, then you would have square root of n is this number times s over that margin of error, and then you just square both sides. So that way n is all of this squared. Then, for example, for this setup that I have right over here, I could say, since I wanted my margin of error to be no bigger than 0.1, and maybe my standard deviation was 0.5 or something, and then that t sub alpha over 2, maybe it was, I don't remember, 1.65, something like that. All this would get squared. About 68.06. So if I had a sample that was any bigger than that, it'd be a waste of resources if this is as accurate as you need to be. If I look at the test statistic, if I look at my regular old test statistic, when I see this, it has the form to me of having some number in the top, and where does n live? It's like in the denominator of the denominator is where I see n. Right? It's in the denominator of the denominator. But the denominator of the denominator algebraically simplifies to just be up here. It's just n. So this computation can really be x bar minus mu over s times the square root of n. They're the same thing. Now, if the mean, if all of this is going to be the same, and all that's going to happen is the sample size increases. If this sample size keeps increasing, it's being multiplied by this, which is staying the same. So then this whole thing would keep increasing. If the test statistic keeps increasing, what's going to happen to the p-value? It's going to go down. Eventually, it will go down so far that we would finally say, okay, we are safe to reject. In the problem with the magnets, we did not reject. However, if the sample size kept increasing, then it will decrease the p-value if everything else stayed the same. Of course, it won't stay the same because the standard deviation will actually start to decrease as well. Because you'll end up having more and more observations where the magnets were not effective. Standard deviation will tend to 0 as n increases. Can you see why the standard deviation would tend to 0 as n increases? Because what is the standard deviation? It was the square root of the variance, and that thing was the square root of the sum of the squared deviations, and then what was down here in the bottom, n minus 1. So if n is up near 1,000,000 or something, I'm going to be taking some bunch of deviations squared, added them up, great. But now I'm dividing by a huge number. And so it will keep shrinking down. I'll keep dividing by something bigger and bigger and bigger, and that standard deviation will keep getting smaller and smaller. So it's a little unrealistic to pose this question, because it has to assume that everything else stayed the same. You can't just, so you could have the sample sizes get larger, but the other numbers will not remain the same. If they did remain the same, then yes, eventually you could have a p-value so small that you would reject. I feel like there was a question somewhere, and I have to hunt around and see if it got removed. But there, once upon a time, like last semester, or maybe the one before it, I can't remember, there was a question somewhere about compute the appropriate sample size. And this is actually something that we'll talk more about on our week 10 Zoom meeting. We'll do this again. So yeah, given some maximum amount of error I'm willing to accept for a specific amount of confidence, if I know my sample standard deviation, I can tell you how many people need to be in the sample. And this is what they would use to decide how many people do we need to have in our study, this computation. BMI statistics for men and women. 0.01 significance level. Now, if I didn't have any data, or let me ask you, what would be inclined to think about BMI for men and women? Are they the same? Are they different? I might think that they're different if I had no access to any data. It seems like every time I've done this problem, though, it comes out that they're the same. So we'll see what happens to you. All right. In fact, it's already working counter to what I expect, because it's got the male BMI higher than the female one. And then the female one has a smaller standard deviation. And what do they want us to check? Do they have the same body mass index? So that would be a two-tailed test where the alternate hypothesis has mu1 different from mu2. When I do my two sample t-stats, put in these numbers. We have 50 of each group. For the males, the average is 28.1021. You're going to have to put in all those digits, 7.550067. And that's the good thing about the options edit, is that you can only type it in once. I've got my test statistic, I've got my p-value. That's a big p-value, that's 11%. 11% chance I'd be wrong if I reject, so I should fail to reject. Failing to reject says mu1 and mu2 are the same. So the evidence that was collected here is not strong enough to say that they have a different BMI. To 3 decimal places, my p-value is 0.118. I will fail to reject. I do not have sufficient evidence. Now they want the confidence interval. So I do options edit, switch it to confidence interval, and I just need to tell it the correct confidence level. Well, my alpha is 0.01, and this is a two-tailed test. So how do I compute my confidence level for a two-tailed test? 1 minus alpha. And alpha is just 0.01, so my confidence level is 0.99. I got a negative lower limit and a positive upper limit. So 0 is in the confidence interval. I'm 99% sure that the difference between the BMIs of men and women could be 0. Could very well be 0. So to 3 decimal places, minus 1.391. And positive 5.569. Does it support the conclusion? Yes. Confidence interval will always support the conclusion. In this case, it's supporting it because it contains 0. Here's those words again. Do not assume that the standard deviations for the populations are equal. That would mean that the variance, the population variances, are unequal, and we would have to use that complicated degrees of freedom. In other words, I could go out to some random website on the internet that claims to be able to compute for me the test statistic and p-value for a difference of 2 means. And I will get the wrong answer in most cases on most websites because they'll all be assuming equal standard deviations. And what am I checking? What is going on here? Lead levels in your blood. That's probably not good to have lead in your blood. And somehow it's going to affect your IQ. And I wouldn't think it's going to make you smarter. But I really don't know. I'd have to conduct my test first to see. Does having lead in your bloodstream lead to different IQ scores? So test the claim that the average IQ of people with low blood levels is higher than the IQ of people with high lead levels. So that would be mu1 greater than mu2. I need my test statistic. So go to Options Edit. And for group 1, the average IQ was 92.84321, with a big standard deviation 15.12803. It's an awful lot of digits for an IQ score, probably not that, critical. However, I'm just going to type in all the numbers they gave me, so that way there's no risk of that being a problem. Looks like they had a hard time finding people with high levels of lead. We only had 28 of those people, but that's okay. The populations, or the sample sizes can be different. They can be wildly different. And I'm doing a hypothesis test with mu1 greater than mu2. I've got my test statistic, I've got my p-value. So my test statistic is 1.99. And the p-value is kind of big. Or I mean small, excuse me. 0.025 to 3 decimal places is 0.025. So that's not a very big probability of being wrong. So I'm going to go ahead and take the risk and reject it, because there's such a low chance of me being wrong. I will reject. Anytime I'm rejecting, I have sufficient evidence. In this case, I'm supporting the alternate. I have sufficient evidence to reject, in which case I shall support the alternate. Construct the confidence interval. I'll go back to StatCrunch, Options Edit, change it to confidence interval. Now this was a one-tail hypothesis test with an alpha of 0.05. So what's my confidence level? My lower and upper limits are both positive. So I'm 90% confident that whatever the difference is between IQs of people with high lead levels and people with low lead levels and high lead levels, that I'm 90% confident that that difference is positive, and it's in between these two numbers. So to 1 decimal place, now they're down to 1 decimal place with the, they got like 5 decimal places in the other stuff. And now it's down to 1, so somewhere between 0.8 IQ points and 8.9. Does it support it? Yes, because the confidence interval contains only positive numbers. So
I have no idea what's going on. I put in the p-value, I rounded to 3, and it's saying that it's wrong. Everything else before is just right, so I don't understand how it's possible.
It's saying the p-value is wrong?
Yes.
It's because you didn't pick the correct. You probably have, not equal selected when it needed to be greater than, or you have,
Yeah, that's probably.
because if the test statistic comes out right
Yeah.
and the p-value comes out wrong, that's what's the issue.
That's exactly right.
Okay. That's it for today. That's it for the class, really. Because this is the end of the new stuff. All right? Next week, we're doing the signature assignment and the final assignment. And then we're good, except for a week 10 week.
So if I don't understand, it's due, listening to do just, right?
No, we're gonna take it in here.
Oh, we're taking the next class, okay, so you don't do it with the next class.
Yeah.
Because they're showing that it's due, Monday the 29th.
Yeah, I'll have to change it.
Okay.
I'll have to change it. Yeah, we'll do it together in here, and we'll do the signature assignment also. So bring the printout. And that's it. So we will have that week 10 Zoom meeting, but it won't take long. We're scheduled for 2 hours, but